Hello everyone, welcome to quick revision series of strength of materials. In this video, I will be discussing about elastic constants and thermal stresses. First, I will be discussing about definition of stress, strain and types of stresses. Next, about Hooke's law. Next, I will be discussing about elastic constants. Next, volumetric and linear strains of some standard cases. Next, what is thermal stress, and next, impact factor. Now, let's see what is stress. Stress is nothing but the internal resistance offered by the body against deformation. This stress is given by load per unit area. This is external load applied on it, and A is area of cross section. There are two types of stresses, normal stress and tangential stress. If that particular stress is normal to the cross section, then that stress is known as normal stress. If it is tangential to the cross section, then that particular stress is known as tangential stress. There are two types of normal stresses, direct normal stress and bending normal stress. Now let's see what is direct normal stress. If we take a bar, suppose there is a tensile load acting on it. Because of this tensile load, there will be a tensile stress on the cross section given by P by A. This particular stress is known as direct normal stress. Now, bending normal stress is generated due to bending action of the beam. For this bending action to happen, we apply axial load only, but in this case, axial load will be eccentric loading, to eccentric loading. Because of this eccentric loading, there will be a moment generated. Because of this moment, the beam bends, and because of this bending action, there will be a bending normal stress. This bending stress varies this way, with maximum at the surfaces and zero at the center. This thing we will be discussing in detail in bending stress chapter. Now, let's see about tangential stresses. There are two types of tangential stresses, direct shear stress and torsional shear stress. In case of direct shear stress, this is generated due to shear force. If we take a particular beam, if there is a load acting here, the direct shear stress is between these layers of this beam, whereas torsional shear stress is generated due to torsion. If we take a cantilever beam with circular cross section with torsion, this shear stress is generated this way along the surface, with maximum at the top, zero at the center, this way. This thing we will be discussing detail in torsion chapter. Now let's see what is strain. Strain is nothing but deformation generated due to applied load by original dimension. If that deformation is in normal direction, then that strain is known as normal strain or longitudinal strain. Here, in this case, the deformation is in normal direction. Then, strain is given by delta L by L. If deformation is due to tangential force or shearing force, then that particular strain is known as tangential strain. In this case, this is deformation and this is dimension. In this case, shearing strain is given by delta by L. Now, let's see what is Hooke's law. First, let's see assumption. For material to follow Hooke's law, it must be elastic, homogeneous and isotropic. And the statement of Hooke's law is stress is directly proportional to strain. Stress is equals to Young's modulus into strain. Here, E is known as Young's modulus. If we take shear stress is proportional to shear strain. In this case, the proportionality constant is shear modulus. This is shear modulus. We know the stress strain curve of mild steel. It looks something like this. In this case, we know that OA is known as proportionality region. This Hooke's law is valid in this OA region. If we see, this is linear part of stress strain curve. That means it's in the form of y equals to mx. In this case, y-axis is stress is equals to m into, in x-axis it is strain. In this case, the slope is given by Young's modulus. In assumptions of Hooke's law, we have seen that Hooke's law is valid for the material which is elastic, isotropic and homogeneous. Now let's see what is isotropic material and what is homogeneous material. If we take a particular material, if it has same properties in one direction, then that particular material is known as homogeneous. If in a particular material, if we take a particular point in all the directions, if it has same properties, then that particular material is known as isotropic material. Combining these two, that means for Hooke's law to be valid, that particular material will have same properties in all the directions and at every point. Okay. Now let's see what is anisotropic material. Anisotropic material is exactly opposite to that of isotropic material. It is material which has different properties in all the directions. That means the properties, if we take a particular point, the properties will not be same in all the directions. In case of isotropic, all the properties will be same. In case of anisotropic, it won't be same. Whereas orthotropic is nothing but which has different properties in perpendicular directions. Remember, different properties in perpendicular directions. It has different properties in like x, y, z directions. Now let's see number of independent constants required to define a particular material completely. In case of isotropic material, we need 2 independent constants. In case of orthotropic, 9, and in case of non-isotropic, it is 21. These numbers are directly asked in exams. Now let's see what are the types of elastic constants. There are 4 types of elastic constants: Young's modulus, shear modulus, bulk modulus and Poisson's ratio. Young's modulus is given by normal stress by normal strain. Whereas shear modulus is given by shear stress by shear strain. Bulk modulus is given by normal stress by volumetric strain, which is this concept of bulk modulus is used in case of hydrostatic loading. See, this is an example of hydrostatic loading. A 3-dimensional body subjected to equal loads in all in all the directions. Okay. Now let's see what is Poisson's ratio. Poisson's ratio is given by lateral strain by longitudinal strain. With negative sign. See, now let's see what is the range of Poisson's ratio. For engineering materials, the Poisson's ratio will be in the range of 0.5, but universally it will be in the range of -1 to 0.5. We have seen what is Poisson's ratio. These are some standard materials and their Poisson's ratio. In some exams they are asking these values. So it's better to remember. Now let's see relation between elastic constants. These are the four relations between these four elastic constants like Young's modulus, shear modulus, bulk modulus and Poisson's ratio. In exam they will be asking questions like they will be giving Poisson's ratio and shear modulus and they will be asking Young's modulus. In some questions they will be asking Poisson's they will be giving Poisson's ratio and bulk modulus and they will be asking Young's modulus. In some cases they will be giving this and this and they will be asking this. Better remember these formulas. Now let's see what is volumetric strain of a three-dimensional body subjected to three stresses in x, y and z direction. Here sigma x is nothing but strain in x direction, which is given by sigma x by E minus mu sigma y by E minus mu sigma z by E. Here we will see why this minus sign has come. See, if we take a particular body, if stress is acting in x direction and if we calculate strain in x direction, this strain will be like there will be an elongation in this direction. So here we consider positive. This is strain due to stress in x direction, whereas if there is force in y direction, this generates elongation in y direction, whereas compression in x direction. So this is generating a decrease in length. So we are considering it as negative. Similarly, in case of z direction, okay. Similarly, we will be writing like strain in y direction and strain in z direction. Volumetric strain is given by strain in x direction plus y direction plus z direction. Summing up all this, we will be getting volumetric strain as this one 1 minus 2 mu by E into sigma x plus sigma y plus sigma z. This formula must be remembered. Now let's see what is volumetric strain in case of solid circular bar. Volume of this cylinder is given by pi d square by 4 into length. This is dimension L. Now applying log on both sides and differentiating it, we will be getting dV by V plus dV by dV equals to 2 times dd by d plus dl by L. Here in this case dV by V is volumetric strain, which is equals to 2 times dia strain plus this strain is nothing but lateral strain plus longitudinal strain. Remember, while using this formula, if they give tensile load, longitudinal strain will be positive and lateral strain will be negative. Don't forget the sign convention while using this formula. Now, in case of spherical body, volumetric strain is given by 3 times dia strain. Now, let's see what are the axial elongations of some standard cases. Now, let's see this. In this case, there is a tensile load P acting. This stress is given by P by A, whereas strain is given by delta by L. We know that stress is equals to Young's modulus into strain. That means P by A equals to delta by L into Young's modulus. That means we will be getting delta as PL by AE. This is one of the most important standard case like they will be asking in exams. Now let's see this case. In this case, we will be getting delta as 4PL by pi d1 d2 into E. d1 is dia of this cross section and d2 is dia of this cross section. And now I will be saying how to remember this formula. Delta is PL by pi d1 d2 by 4 into E. We know that delta is PL by AE. See, in this case there are two dias. See, area is in the above case area is given by pi d square by 4, like if it is a circular cross section. Here, in this case, there are two dias. Remember this way, d square is written as d1 into d2. Okay, delta is PL by A into E. This is not like derivation, I am saying this as a trick. Now, let's see this case. In this case, there is a square cross section with dimension b1 and like other square cross section with dimension b2, and thickness of this is constant. Then elongation is given by PL by b2 minus b1 into TE into ln of b2 by b1. Okay. Now, let's see this. In exams, generally they will be asking find the reaction at supports A and B by giving forces in between. We can follow normal procedure by writing equilibrium equation for this part and writing compatibility equation for the whole system, and we can find. This is the normal procedure. It takes time. Now, I will be saying some small tricks so that solving this type of problems will be easy. If load is given in this direction, RA and RB will be in this direction according to this trick, and RA is given by P into B by L and RB is given by P into A by L. That means RA is given by dimension which is far to A by L, and RB is given by dimension which is far to B, which is A by L. Now, let's solve one problem using this trick. Now, let's find RA and RB using this trick. Writing RA, see, in this case, W is acting in this direction, and writing RA for this force, we will be getting according to the trick W into 12 by 3 by total length. As this force is acting in this direction, RA will be in opposite direction to this, whereas due to this force, RA will be W into L by 3, which is this dimension, by length. Because force is in this direction, RA will be in opposite direction to it. Solving this, we will be getting RA as W by 3 in this direction. Similarly, writing RB, W into 12 by 3 by L due to this force. As this force is in this direction, RB will be due to that force in opposite direction, which is this, plus W into L by 3, which is due to this force, by L. As this force is in this direction, RB will be in this direction due to that particular force. Solving this, we will be getting RB as also W by 3, which is in this direction. So, we got RA as W by 3 and RB as W by 3. Now, see this. See, the sum of forces in x direction is 0. See, we got W by 3 in opposite direction. So, this particular thing is in equilibrium. Okay. This is check. Like, see, this, sum of all the forces on this particular bar should be 0. See, if it is not equals to 0, like this bar should be moving, which is not possible. So, first of all, check this. Sum of all the forces should be 0. Now, let's see thermal stress concept. In this particular bar, L is dimension of length, B is dimension of breadth, and H is dimension of height. Due to increase in temperature of delta T, the change in length is given by L alpha delta T. Okay. Then strain, we know that strain is delta L by L. That means strain is alpha delta T. Okay. In this particular case, this end is free. That means if there is temperature increase, it is free to expand. There won't be any stress generated. In this case, stress generated will be 0. Whereas in this case, there is an increase in temperature, but this can't move. the movement in this direction, I mean at this support is, the movement is restricted. So there will be a stress generated due to this restriction. This stress is given by strain generated here into Young's modulus, which is equals to E alpha delta T. Remember this directly. See, in some questions they won't ask directly in this manner. They will be giving a fixed support, I mean both sides fixed support, and this support can move up to a distance delta, and after that it is restricted. In this case we can't use this formula directly. So if we follow these steps, we can do any type of problem. If we remember this formula can't be used in all types of problems. So if we follow step by step procedure, it will be easy. Now let's see this case. In this case, first step is we have to calculate the total expansion. See, if there is an increase in temperature of delta T, the total expansion will be L alpha delta T. Okay. Second step is we have to find the expansion restricted. If the total expansion is L alpha delta T and it can expand up to delta freely. So expansion restricted is L alpha delta T minus delta. Then strain restricted will be expansion restricted by dimension of this length, I mean of this bar. Next, we got strain as this value. Now we have to find stress. Stress is given by strain into Young's modulus. This procedure, I mean if you follow this step, 4 steps, when they ask stress, in any type of problem we can solve easily. Instead of remembering this formula, we can follow these 4 steps. Now let's see this. This case we have seen just before. In this case, it is a 3-dimensional body. There is restriction in 2 directions, that is in y direction and in z direction. In x direction, it is free to expand. Now, the stress is given by alpha Te by 1 minus mu. We can easily derive this also. See, in y direction, there is restriction in strain. This strain is given by alpha T. We know that the strain in y direction is sigma y by E minus mu into sigma x by E minus mu into sigma z by E. In this case, sigma y and sigma z are equals to sigma. By substituting this, and sigma x equals to 0 because in x direction it is free to expand. By substituting this, we will be getting sigma as alpha Te by 1 minus mu. Okay. Now let's see this case. In this case, the strain is restricted in x direction, y direction and this z direction. In this case, sigma is given by alpha Te by 1 minus 2 mu. We can easily derive this case also. See, same way, writing sigma y is equals to alpha T is equals to sigma y by E minus mu sigma x by E minus mu sigma z by E. In this case, sigma x equals to sigma y equals to sigma z. There is no free expansion in any direction. So, there won't be, like in this case we have free expansion in x direction. So, sigma x is 0. In this case, there won't be, like all the stresses will be, like we will be having all the stresses. There won't be any 0 stress. So, we will be getting alpha T as sigma by E into 1 minus 2 mu. Solving this, we will be getting sigma as alpha Te by 1 minus 2 mu. Okay. Now, let's see thermal stresses in composite bars. In this case, there is a composite bar with steel and copper and there is an increase in temperature. Our aim is to find thermal stress in steel and copper, that is sigma C and sigma S. This is a composite bar and this is firmly fixed. See, now if we increase in temperature, there will be an increase in length in both steel and copper, but steel has less thermal expansion than copper. That means steel will expand less compared to copper, but this is firmly fixed, so they both get adjusted at some particular length. In order to achieve this length, there will be a tension in steel and compression in copper. Okay. Now we found in which bar there is compression and which bar there is tension. And next we will be writing like force equilibrium equation. See, these two forces must be equal. That means this tensile force must be equal to compressive force. This tensile force is equals to compressive force. This force is given by stress in steel into area of cross section of steel, which is equals to stress in copper into area of cross section of copper. Okay. Now we will be writing compatibility equation. See, finally they both are expanding equally. I mean, final expansion of both steel and copper is same delta. That means final expansion of steel is given by total expansion of steel due to temperature change, that is L alpha T, plus expansion due to this force T, that is T into L by area of steel into E. Okay. This is actual expansion of steel, this one. Actual expansion of copper is given by, see, L alpha delta T is this one, and in this case, in case of copper there is compression force, that means there is decrease in length. That means L alpha of copper into this is due to increase in temperature, plus due to compressive force there will be decrease in length, minus of that compressive force into L by As into E. By substituting in second case, if there is, similarly in case of decrease in temperature also we can find. See, same bar, have taken same bar. Now there is decrease in temperature. See, same as increase in temperature, there will be more decrease in case of copper. If copper comes still here, there will be less decrease in case of steel, because steel has less coefficient of thermal expansion than copper. Okay, but finally they both get adjusted at some point in between. So copper there will be tension, and in steel there will be compression. Okay, this will be opposite. In case of temperature decrease, in steel there will be compression, and in copper it will be tension. Next we can write this equation, and next we should write compatibility equation. See, while writing compatibility equation, there is a decrease in length, minus of L alpha delta T, and in case of copper there is compression, so minus of compression into L by AE. Whereas while writing compatibility equation of copper, it will be minus of L alpha delta T. There is tension, so plus T into L by AE. This is tension, this is compression, and this is tension. Okay. By like before case only, by solving we will be getting what is I mean stress in steel and stress in copper. Okay. See, if we have numbers and if we substitute them, this won't look this complicated. We can solve it easily. Okay. See, if they give area of copper as some 20 and area of steel as some 10, directly we will be getting stress in copper as stress in steel by 2. By substituting stress in steel copper as stress in steel by 2 in second equation, directly we will be getting stress in steel, and by knowing stress in steel we can find stress in copper. Now let's see this case. In this case The steel and copper are placed one after the other between two fixed supports. Now, first thing we have to remember is this system must be in equilibrium. For this system to be in equilibrium, these two reaction forces must be equal and in opposite direction. Unlike before case, if there is increase in temperature, see, the expansion is restricted both in steel and copper. There will be compression in both steel and copper. Okay. In this case, compression will be in both steel and copper in case of increase in temperature. This is equilibrium equation and this is compatibility equation. Now let's write this compatibility equation. If we draw the free body diagrams of steel and copper, there is an increase in temperature. Due to increase in temperature, the steel will expand, which is equals to L of steel into alpha of steel into delta T, and there is compression. So, due to this force, this compressive force, there will be a decrease in length, that is R into L by AE. Similarly, in case of copper, it will be like this alpha into this L alpha delta T is due to increase in temperature, and this RL by AE is due to this compressive force. This is compatibility equation. Total expansion in steel plus total expansion is in copper is equals to 0. By substituting this in this equation, we will be getting stresses in copper and steel. See, R by A is nothing but sigma S. If you confuse how will we substituting this, R by A is nothing but sigma S. Substituting sigma S in terms of sigma C, we will be getting sigma C. After getting sigma C, we can easily find sigma S. Now, let's see what is impact factor. In general, there are three types of loading: gradual loading, sudden loading and impact loading. Gradual loading is nothing but increasing a load from 0 to certain value, whereas sudden loading is nothing but if we take a particular weight W, placing it suddenly and there won't be gradual increase. Okay, whereas impact loading is nothing but throwing a certain weight from certain height. Okay, in order to find relation between stress generated due to sudden loading and gradual loading or impact loading and gradual loading, we will be using impact factor. Okay, suppose if they ask delta generated due to impact loading, this load is thrown from height h. So, first we will be finding impact factor by substituting h. We know delta generated due to gradual loading, which is given by, if it is axial load P acting, it is given by PL by AE. By substituting this, we will be getting impact factor. By multiplying this impact factor with delta gradual, we will be getting delta due to impact factor. Similarly, for finding stress due to impact load, we will be getting stress due to gradual load into impact factor. Okay. See, now let's see impact factor in case of sudden loading. In case of sudden loading, it is kept like normally it is kept on the beam. That means this height will be 0. So, substituting h equals to 0, we will be getting impact factor as 2. That means in case of sudden loading, impact factor is 2. So, delta due to sudden loading is given by 2 times delta due to gradual loading. Okay. With this, I will end this video. If you find this video useful, share it with your friends. Thank you.